Hello guys, welcome to our next video in the playlist Google Earth Engine for the forest resources. So in today's video, we're gonna see how we can build a entire carbon stock estimation model. So without any field data, we're gonna estimate what's the upper biomass density at a particular region of interest, and we're gonna use some of the machine learning algorithms with non-linear regression output in order to predict the above biomass density at a region of interest, and later you can convert it into carbon stock for a region. So with the use of some of the conversion factors, carbon conversion factors such as 0.47 for usually for above ground biomass density. So once you get the above ground biomass density, you can derive the below ground biomass density based on the vegetation type, and you can get the total vegetation carbon stock at a particular place. So without any kind of field data, so we are gonna do build a model, and we're gonna see how we can do this. So let's just start with defining our region of interest. So I have zoomed my map catalog into one of the great regions in the Karnataka near the Uttara Kannada. It's on Western Ghats. So I have taken already defined my region of interest as I will define my region of interest. So you can just take this, draw a rectangle. So I'm taking this part as my region of interest, and you can just check it out. So here you can see my region of interest is imported. So if you want, you can, instead of geometry, you can convert this into a feature collection, and you can add a property if you want. If you don't want, you can just delete it and click on OK. So instead of geometry, I want this to be as my region of interest, ROI for short. So now you can see this is my region of interest. So now let's just add one function to zoom the map to my region of interest every time I run the script with the help of function map dot center object to ROI. So just click on the run. So here you see it's automatically zoomed into my region of interest. So I will also want to add my region of interest map with the help of function map.addLayer ROI. So I want to style it with the help of function.style. Specify the color which you want. So my color will be black for outline, and I want the fill color to be transparent. So I'm using the octocode. So this is the octocode for transparent fill color. So again, I will rename it as my ROI and just click on the run. So you will get your beautiful region of interest, which is loaded into your map catalog. So if you want, you can zoom it a little bit, or else this will be fine. Yeah, so this I'm doing to adjust my zoom factor. So if you can just click on the inspect column, here you will get the zoom level. So the zoom level is 11. So I'll just go here and fix it to 11. So by doing this, I don't have to zoom and rotate my map again and again. So I have fixed my region of interest whenever I run the script in order to check. So it will be there only. It's automatically zoomed in with the help of map.center object. So next, we will import our Sentinel-2 data. So this is our main independent variable. So out of this, we will derive the indices, and we will project the evergrown biomass density with the help of these Sentinel-2 bands, as well as the variables, as well as the indices which we derive from it. So I'm importing this harmonized Sentinel-2 multispectral instrument level 2A. So here you can rename it as S2 for your convenience, and I'm gonna uh, comment some of the line in order to better understand the script. So it's always a better practice if you just write down what the next code do. So I am here writing the Sentinel filtering and Sentinel filtering and derivation of indices. So now create a variable called pre-image. So for the pre-image, I am filtering my Sentinel-2 with the help of function filter bounds. First, let's filter it to region of interest. So in order to clearly know how this filtering works, so let's just print this pre-image. Uh, pre-image. Okay. So click on the run, come to console. Here you will see your image collection is computing. So when there is a filter bounds filter is applied, you have seen this has 792 elements for this region of interest. So when the satellite has launched for this region of interest, we have this much of elements. So I have only entered the filter bounds function in order to filter my image collection to my boundary, that is my region of interest. So now I want to filter the date also, so I'll use one more function dot filter date. So I want to build my model for the 2024, because whatever my ground biomass density is there, it's available for 2024 itself. So for the 2025, it's not yet published. So I'm gonna use 2024 the entire range as my uh, pre-image collection. So now if you can see, I have entered the filter date function. So now the image collection has reduced from 792 elements to 116 elements. So for this region of interest, I have 116 elements, that is the images which is available for my region of interest and for the year 2024. So you have been thinking what's this 2025? So this is an end date. So if you can just go and check the docs with the help of filter date. So here you will see for image collection you have a filter date. So it's take two arguments, start and end. So if you can just see the end start date and end dates may be in the form of date in this form, and here you can see the end date is optional and it is exclusive. It means, between inclusive and exclusive, so the end date is exclusive. So whatever the date you give, that is exclusive, it is not included in your image collection. So if you can also want to check, if you can just scroll down, here you will get your last image collection will be 2024 December 29. So this is your last image collection, last image. So there is no images from 2025. So that's how dot filter date function works. So I hope you have got this. So after filtering to date, now I want to filter for my cloud cover also, the most important one. So without cloud filtering, you cannot do anything. So again, with the use of function dot filter, ee dot filter dot less than. So I'm using this less than function. So I want to filter the property. So the syntax is, first you mention your property and next mention what is the value you want to filter. So the property for the cloudy pixels in the Sentinel-2 is cloudy pixel percentage, and here you can enter the value to be less than 1%. So you may be wondering how I got this property name. So you just have to go to the Sentinel-2, and if you come to the image properties, here you will get all the properties associated with this image collection. What is the data type and what's the description? So here you see the cloudy pixel percentage. So remember to use this underscores. So it is also called snake's case. So it is a granular specific cloudy pixel percentage taken from the original metadata. So this particular property you have to filter, so you can just copy this and paste it in here. So if you have doubt with your spellings, so now I have filtered for my cloudy cover percentage also with a less than 1% of cloud cover. So here you see now my filtering is done. I have 17 elements which are valid entire for the entire year of 2024 for my region of interest with clear clouds. So that's how you can filter Sentinel-2 image with only 3 lines of code. So that's the power of the Google Earth Engine. So now what I have to do, I have to scale my Sentinel images. So I have filtered it down. I have filtered for the date and cloud cover. So now I want to create one more variable called image. So here I am applying for the pre-image. I'm going to map a function. So this mapping will apply a function. So I'm creating one more function, so which will take inside an image and it has to return something. So this is the syntax for creating a function and mapping a function. So I have applied it in the one line only. So here you can see this is a separate, you can create a function separately, then you can map this to your image collection. So remember, mapping works only on a collection of data set like a feature collection or the image collection. So if you go and apply it for some uh, image or a single element, then the mapping would give a error. So you can also map a list, you can also map whatever the collection it should be have. So you can also map an array, so based on the function. So now we are defining a function which will take a image as an input and it should return something. So from where will I start? So I will first scale my images. So I'll create a one more variable called scale. So I'm writing all this inside my function. So what is scaling? Is that if you just go to your original metadata and here you find the bands. So the bands name you have B1, B2, and what is the description? So B1 is aerosol, the B2 is blue, the B3 is green, red is 1, 2, 3, near infrared, red is 4, yes, short wave infrared, speed 1, speed 2. So all these bands are there with the respective resolutions and with the respective wavelengths. But at the last column here you will see one more you can say property is that scale. So the scale is 0.0001. So it means that in order to carry out analysis with the use of Sentinel-2, you have to multiply each band with 0.0001, because the original band reflectances will be in from 0 to 3000. So why the Sentinel-2 or the Copernicus organization do is like that? Because for storing an integer data type takes a less storage rather than storing a float data type. So if you go for storing a float data type or float 64 or 32, then it would require more storage. So hence they will store everything in the integer, then they will give the user what is the scale value you have to multiply to carry out the analysis. So first you need to multiply the scale value, then you go for the analysis. So in order to get clear things, I will show later how does that work. So as of now, we will create one more variable called scale, so that for my each image which I have taken as an input from here, it has to be get multiplied by 0.0001. That's it, my scaling is done. So now I have to create all the indices which will be given as an input to my model. So I want to create first uh, uh, indices, that is NDVI, the most common global indices which is used very often. So from my scaled image, so remember from here I'm using my scaled image, I'm not using the original image which I have taken as an input from my pre-image collection. I'm using the scaled image because now whatever the analysis or whatever the indices we are going for doing, so all that have to be on my scaled image. So I have to take my scaled image as an input and I have to do the calculations. So you know, for the NDVI it's a normalized difference between near infrared and red band. So there is a direct function to calculate a normalized difference. So if you can just search this normalized difference, here you see on an image object you have normalized difference function which will take a band name and computes the normalized difference between those two bands. So it will be computed as first minus second and divided by first plus second. So what are the arguments it need? It need an input image and it need a list of bands. That's it. So please try to read the documentation. So the documentation is like a bible. So whatever you have doubt, always go to documentation, see the syntax, what the input it's taking, in what type of input it is taking. So see here they have mentioned clearly it should be a list. So instead of list, if you pass a string object or a tuple object, then it won't accept. So that's why reading a documentation is a skill. So you have to go through the documentation before going for use of any function. So now for my scaled image, I'm going to use my normalized difference. So one shortcut is that you can always press Ctrl plus space in order to autofill the functions. And I have to give the band name between V8 and B4. So B8 is my near infrared band and B4 is my uh, red band. So I also want to rename it as NDVI. Okay, so now my index is calculated. So next, what I have to do, I have to create one more variable. So I'm gonna use a variable the n number of indices, because as much as your input feature contains the indices, it is easy for the model to go for predicting the relationship between the dependent and independent variable. So now I will create one more indices that is called as uh, the particular vegetation indexes. So P perpendicular vegetation indexes, which is called as PVI. So PVI is just a normalized difference between same the near infrared band, but it will take the red edge band instead of simple red band. So I'm gonna use this scale dot normalized difference between B8 and B5. So B5 is my red edge band. So here you can simply name it as PVI. So if you have any kind of doubts regarding the band number and band names, again go to the documentary of the image collection. Here you can see B4 is red, B5 is red edge 1, red edge 2 is B6, red edge 3 is B7, and near infrared you have B8. So there are four red edge bands and two short wave near infrared bands and one near infrared band. So remember, so the band names. So next we will go to calculating again different types of indices. Next is our the chlorophyll red edge index, so CIRE. And the formula for this is you have to divide the near infrared by red edge band 1 and you have to subtract it by 1. So I'm going to use the expression for this, or you can also simply go for dot divide and dot subtract function, but I want to show you the help of the expression button, so expression function. So I'm just using the function dot expression. So if you can just click on the control plus space, it will automatically fill what are the inputs it require. So for inputs it require an image absolutely, and you should write an expression and you should map what the expression contains. So for details you again go to the documentary, click on expression. So here you will find image dot expression. So see, it takes the two input expression and map. So this will evaluate the arithmetic expressions on an image, so possibly involving additional images also. So here you can see it need an expression and a map of input images which is available by name. So you will, and this should be in the form of dictionary, so and this should be in the form of string, so that's more important. So once you see this you will understand. So first I will write the expression. So it should be near infrared has to be divided by the red edge. You can simply just take red edge 1, and you can just close the brackets and it has to be subtracted by 1. So my expression is ready and I want to map things now. So remember, mapping should be a dictionary. I have shown you in the documents, and here you should just name what is NIR, because the expression should know what should I apply for the near infrared band. So I will say from the scaled image you just select this this B8, and again similarly for my red edge 1 you go to my scaled image and you just select from my B5. So that's how the red edge 1. So you don't have to specify what is 1 is, because the expression is able to parse what 1 is, and it will automatically subtract this 1 from it will automatically subtract, and it will automatically divide the NIR and near infrared band also. So that's the power of Google Earth Engine expression function. So I want to also rename as CIRE, the chlorophyll red edge index. So I have calculated 1, 2, 3. So 3 indices. So we'll calculate 2 more. So I'm simply going for the red edge simple ratio. So short for SRRE. It is called as the Redditch simple ratio. So the formula for this is you have to divide Redditch 3 by divided by Redditch 1. So here I will directly use the dot function. So here you can just take from the scaled image, you just select my Redditch 3, which might be I think a B7, so I'm not sure. So let's just go to documentary. So here you will see B7, yeah, Redditch 3, and it has to be divided by Redditch 1, that is my B5. So I'm just directly using the function dot divide, and inside that I'll give the band name. Again, from the scaled image you select this B5. So and directly you rename it as SRRE, the Redditch simple ratio. So next I will calculate the Mary's chlorophyll terrestrial index, MTCI, Mary's terrestrial chlorophyll index. So you just have to specify the variable name, and you again have to go for the scaled image, and you click on the expression and you write down the expression, what's the expression you want to calculate. So here the formula is red edge 2 has to be subtracted by red edge 1, and it has to be divided by again the same red edge 1, and it has to be subtracted with red edge. So this is the function this is the formula for calculating the Mary's chlorophyll terrestrial chlorophyll index. So after that I have to map my variables. So what is red edge and what is red edge 2? So you can just simply say red edge 2. From my scaled image you select the B, red edge 2 is B6, and for my red edge 1, go to my scale image and select B5, and again for my red band you go to my scaled image and you select B4. So yeah, my mapping is done. So I'll just rename it as MTCI, the Mary's terrestrial chlorophyll index. So I think this much is enough. So you can also add a number of indices like the NDWI in order to detect the water bodies. So NDWI will also detect the water bodies. Whatever the negative values are there, it will be defined as an water. So apart from that, you can also calculate bare surface index in order to know what is the bare surfaces, highlight the bare surfaces out of the Sentinel-2, and you can also calculate the sorry, the modified soil adjusted vegetation index. So where there is a more highlight of soil, so you can go for calculating those indices. So since my region of interest consisting of mostly the forest lands, so I'm particularly interested in getting the vegetation, so I'm using all these vegetation indices such as NDVI, the perpendicular vegetation indexes, and CIRE, the chlorophyll red vegetation indexes, the short red vegetation indexes. So all this I'm calculating. So now I have to return. So what should I return? So I will just take my scaled image and I will add the bands with the use of function dot add bands. So it has to be a list. So I will add my NDVI, I will add my PVI, I will add my CIRE, SREE, MTCI. So you can give a variable whatever name you want, but you just have to be sure what you have given. So that's most important. So now I think it's clear to you. So I have filtered my image collection. I have scaled my image with the use of function image, and I have calculated the indices, and I have written my scaled image with added bands of NDVI, PVI, MTCI, etc. So now I will create a median composite of it here only. Just press dot median. So whatever you had 17 elements, now it will be compressed a single image, taking the median reflectances out of it, and will also clip it to my region of interest with the use of function the clip. So with the use of function dot clip. So now my filtering is done, my scaling is done, all my input features are ready. So in order to show what does my input feature contains, I just want to print this image and click on the run. Here you can see the object type is an image, so it consisting of 31 bands. So I'll show you what are the bands are. It is from B1 to B12. Those are my electromagnetic spectrum bands, starting from visible to up to short wave infrared. So apart from that, you have AOT and WBP. So these are all the quality and mask bands. So Q8, 10, Q8, 20, 60. So if you want, you can remove all these bands because they are of not much importance for your model. It might create confusion for your model to figure out how to relate these bands to my output ground biomass density. So that's why we have to remove these bands. So if you see at the last, you will see our indices bands. So NDVI, PVI, other bands have been added as a band. Our indices has been added as a band. So now we just have to remove this non unwanted band. So how I can do that? We just come to our pre-collection here. So I'll just use the function dot select. It's helping in selecting the bands. So you just have to use b dot star. So why star? Because I want all the bands which are starting with the B, and for star you can take whatever the 1 2 3 4 is there, you can take that, and you can just simply click on the run. So now again it will compute an image in the console. Now you see instead of 31 bands, I have 17 bands in here. So it's just having the B bands from B1 to B12, and it also have NDVI, whatever the indices I have calculated. So these are the set of 17 bands which I have for predicting my ground biomass density. So apart from the sentinel vegetation sentinel optical indices method, so you know the optical indices, radar indices, the radar remote sensing type. So the sentinel will work in the uh, what you can say in the visible, near infrared and short wave infrared wavelength. But we can also make use of radar vegetation indices, so that we will be giving as an input. So here instead of image, you can just rename it as optical image, because we are going to have radar image also. So here also you can rename it as optical image. Optical image. Yeah. So this is one of the part of my features. So next I'm going to use my radar indices. So here you can just write the comments. So it's always a good practice to write down the comments. So I'm taking radar indices calculations. So I'll be using Sentinel 1. So just go to here, Sentinel, and here you can find Sentinel 1, the SARGRD. So working on the C band synthetic aperture radar. So at 5 gigahertz of the wavelength. So it is available from 2014 till present. So if you can just come to the bands, it has polarization bands. So HH, HV, VV, and VH double cross polarization bands are also there. So all the resolution is in 10 meters. So the units are in decibels. So instead of decibels, you need to convert it into the backscatter coefficients. So in order to carry out the analysis, you have to convert this into backscatter coefficient by taking the log of each band. So we will also see how can we do that. So you just have to import this, and you can rename it as S1. So after all this, now I will creating a variable called S1. and not this one. So you can just create pre-image SAR, and here also you can just give pre-image optical, and here also pre-image optical, because we are carrying out both optical and radar. So that's why, in order to be clear, I'm using all these functions. So first I have to filter down my radar indices. So just take S1 and usually filter to bounds with the help of function ROI, and just print to know what does it contain, how many image collections it have for my region of interest for the Sentinel-1. Yeah, it has 550 elements. So just go to feature, expand one of the bands, expand one of the images, and you see there are only two bands, VV and VH. So which is particularly useful because whatever my region of interest is, it's mostly a forest area. So vertical transmit, vertical receive, horizontal vertical transmit, and horizontal receive. So useful in detecting whatever the bands whatever we have. So you just have to specify all this. So I don't have to filter anything. You see here we have IW, it means interferometric wide path, and it is ground range detected. So if your region of interest is other than what my region of interest is, so you can just go to the Sentinel-1 and you can come to image properties. So I will tell you what are the properties you have to filter. So you just scroll it down, and here you will get uh, the instrument mode. So the instrument mode should be interferometric wide swath. So you know what swath is if you are from a remote sensing background, and it is also has the extra wide and strip map. So the mostly interferometric wide swath will be good enough for carrying out the analysis. So this is the one property you have to filter it down, that is the instrument mode. So apart from that, you also have to filter, yeah, the orbit property pass. So it has to be ascending and descending, so based on your region of interest. So in my case it is ascending because my region of interest is in India. So it is coming from uh, below. If you imagine earth as a sphere, so it is orbiting polar in a polar orbit. So whatever the region it is surrounded by the Indian or covering by the Indian region, it will be in the ascending mode. So the orbit pass mode will be in the ascending. So I don't have to filter this also. If your region of interest is other than my region of interest, then you have to filter it down to whatever your region of interest is there. So apart from the orbit path pass, so you can also go for this one, the transmitter receiver polarization. So what is how the transmitter should receive whatever the uh, polarization we have passed earlier. So there are combinations like VVHH, VVHH, and HHVV. So I have told you my region of interest. Again, it has automatically filtered for VV and VH, which is good, and we can carry out the analysis. So this is one more property, transmitter receiver polarization. You have to filter for those properties. So next, if you can just go through is only these are very much important. So let's just filter that. So though I don't need that, so for you to know how can you filter that, I'm showing you. So you can use a function ee.filter so should be equal to my first properties. So you can expand it in different properties. So first one, the instrument mode, you just copy this and paste it in here. So my instrument mode should be equal to IW. Now you click on the run. Earlier we had 550 elements, so now also we might have, yeah, you see we have 550 elements only because it's automatically filtered. So ee dot filter,
dot equal to, so take our next property, that is orbit pass should be ascending. Yeah, now you see my image collection has reduced to 119 elements because it has both ascending and descending properties. So after that I need to filter my last one property, that is transmitter receiver polarization. So just click in here. So I don't want to do this because I want both VV and VH. Still, if you give and click on the run, we'll see if there is any image collection. Zero elements. So that's why transmitter receiver polarization should be VV, HH, VV. Okay. So we can select a list VV and VH. Right. Yeah, same 19 elements. So this is how you can filter the properties which I have told you. So after filtering all this, you can just remove this and you can go for the calculation of indices. So now I'm creating a variable called SAR image because we have optical image. Now we have SAR image. So for my pre-image SAR, I'm mapping a function which will take image as an input and it should return something which we will see afterwards. So now I have told you we have to convert whatever the decibel values to the backscatter coefficient. So if you can just Google here, you will see clearly. So to convert from decibels to backscatter, the interval algorithm, so you have to use the sigma naught formula. So where to the base of 10, the decibel has to be divided by 10. So we have to create an image of 10, and for the decibels image, it has to be divided by 10 again. So that is the formula. So for converting the decibels to the backscatter coefficients. So now here you can create one more variable called sigma because we are converting this into sigma naught. So I'm going to create an image with the constant value of 10, and I'm going to raise the power with image has to be divided by 10 again. So my now my SAR image is in the sigma naught backscatter coefficient values. So it has been converted from decimal to backscatter coefficient value. So now whatever the indices I will derive has to be based on these uh, values only. So first indices I'm going to calculate for the radar indices is my radar vegetation indices, RVI for short. So for RVI, so I'm going to use the expression sigma dot expression. So the formula for calculating the expression is 4 has to be multiplied with VH, and it's better if you use parenthesis, and it has to be divided by VH plus VV. So this is the formula. So you can also map the function. I have already told you. So you have to use a dictionary to map a function. You don't need to define what is 4 is. You have to define what is VH contains. So VH is equal to my sigma. Out of my sigma, you just select this band of VH. So after that, for VV also, I'm gonna define what VV is. So just go to sigma dot select VV. So that's it. And don't forget to remember it is my radar vegetation indices. So next I'm gonna create one more indices called as normalized difference index NDI. So for NDI, I have to go for calculating uh, the scale, not scaled image, the sigma image dot expression. So here you have to give the expression. So it is log to the base of 10. So log to the base of 10. So log 10 has to be with 10 multiplied by VV and VH. So this is the formula for calculating the normalized difference radar index. So I'm just copying this and paste it in here, so you don't have to type always. So but remember here to rename. So this is my NDI. So after doing that, you can also create one more indices that is called as radar indices, RI. So this is just have to be from my sigma image, select VV, and we have to divide it by the same sigma image dot select VH, and rename it as RI, the radar index. So I hope my indices are full, it's enough. So here I have to return my sigma naught image with added bands of the radar vegetation index and my normalized difference index. So it don't has to be a string, it can be variable. So RVI and NDI and RI. So my input feature collections are now well and good. So I just want to print it and see how does it look. So SAR image, click on the run. So you have two input feature, one is optical image, one is SAR image. So it is now showing as 119 elements only because I didn't compute the median composite. So I'll compute the median composite and I'll clip this to my region of interest and click on the run. Yeah, it has 6 bands. So here you can see one angle band also we have, so that is not particularly important. So I will remove it with the use of the function dot select. So you can just simply select here VV and VH. So the two bands I need, I don't want this angle band. So just select this. Now you see we have 5 band and 17 bands in the optical bands. So vertical VV polarization, VH polarizations, which are in the sigma naught now, which are converted into backscatter coefficient rather than in the decibels. And we have our 3 indices calculated, and it is now in my as a single image. So now I have to create one more variable called input features. So here you can just comment these things as my input features stacking. So input features I'm creating. So for my optical image, I want to add bands of the SAR image. So just print your input features and rename it as input features. Now click on the run. So here you will find 17 plus 522 bands stacked into together as my input feature for training my model. So that's it. So your dependent independent variables are ready now. So you have one variable grade, you have one. If you imagine the regression, on the y-axis you have the dependent variable, on the x-axis you have the independent variables. The independent variables are these 22 bands which you will train them for your y-axis. So that will be my above ground biomass density. So now you can also visualize this. So let's just visualize map dot add layer input features, and leave the visualization for defaults and click on the run. So here you will find your inputs are being loaded. So it's purely black in color because I didn't give any kind of visualization. So here you can go for true color visualization with the combination of 432 RGB, and you can stretch the values to 100% and click on apply. Yeah, clearly you can see my region of interest is better greenery. So it's in on the part of Western Ghats. You can see the barren lands also. So it's quite good. My region of interest is quite good. So if you want to visualize radar bands, so you can just come to here and select the band. Any band you can select. So I'm going to select this radar vegetation indices, test values to 100%, and just click on apply. Yeah, you can see the difference between the radar and the optical images. Okay, so there is some problem. So because only half of the image has been loaded, so let's just try for other images of the other bands. If this problem continues, then we have to compromise with our filter. So I think I have to compromise with my orbit pass mode. You just comment it out and now click on the run. So this is how you can adjust your input. So after you just create whatever the variables are, you just have to see, is my variables are good enough, are they fully covering my region of interest. So visualization is a basic part of your skill set. So you just click on the RVI and click on apply. Yeah, I think now my region of interest is covering fully, because earlier it was empty on this side. So still it is loading. So yeah, you have to compromise on this filter in order to cover your region of interest fully. So I have removed this orbit pass mode to be in the ascending. So now I think it contains both ascending and descending uh, parameters. So if you can see, it takes time on loading this vegetation indices. So here you can see clearly the differences. So just go to the palette and to differentiate the vegetation. So yeah, so next we can go for uh, this you can have, but just set it to false, because all the time I don't want to load the image. So this will be at the false range. So now my input features, all my independent variables have been calculated. So now I want to import my Jedi L4A above ground biomass density map, above ground biomass density dataset. So just go here and click on the Jedi L4A import, rename it as Jedi. So if you can just open this, Here you will find the Jedi L4A dataset. So this is particularly derived from the LIDAR, so which is based on the International Space Station. So whatever the inputs, whatever the bands here are there, at a 25-meter resolution, it is giving the Avogadro biomass density in terms of megagrams per hectare. So it is equivalent to tons per hectare. Remember, megagrams and tons are equal. So at every footprint, 25-meter footprint, which are 60, I think 60-meter apart, so they are giving this Avogadro biomass density. So here you can see the 60-meter along the track. There is a 25-meter footprint spaced approximately every 60-meter along the track. So it is based on the International Space Station attached to the Jedi, and again sampling the densest sampling of three-dimensional structure of the Earth with the use of Jedi. So remember, it is a NASA program. The Jedi stands for Global Ecosystem Dynamics Investigation. Jedi. So similar to that, you have uh, L4A. Regarding the L4A, it will give the Avogadro biomass density. So apart from L4A, you have L2B, which will give you the height, the canopy height above the surface. So for predicting the canopy height, so you can use those Avogadro L2A dataset. So now I'm going to create a variable called Avogadro biomass density. So my Jira data set I have, I want to filter it down to my region of interest, and I want to filter it down, filter date. So yeah, here I didn't filter it for date. So that's why we have huge number of image collections. So you just filter date to 2024, 2025. So now we're gonna filter it date to 2024, 2025, and you can also filter to bounds. Then for bounds is done, so you can just map dot add layer above ground biomass density. So this is the visualization parameters we have to provide. And one more thing you can filter with the Jedi dataset is that you can come to the bands, and here you will find some quality degraded flags. So you can just open this, and if you can just scroll it down, here you will find a code snippet. So in order to filter the images, it is provided by Google Earth Engine data catalog itself. So explore with the Earth Engine. So here you will see they have taken one function which will take image as an input, and it will update the mask according to L4 quality flag. The L4 quality flag should be equal to 1. So this will be between 0 and 1, between the 0 and 1. So whatever 1 indicates that whatever the pixels are there, they are very much good in terms of quality. So I want to filter it down to equal to 1, and this degrade flag has to be equal to 0. So that's one function they use, or the quality flags they use for filtering out the quality mask of Jedi dataset. So let's just see, since our region of interest is very much smaller, so if we can filter those degrade flags and quality flags, I don't think we have enough pixels to train our model. So let's just see. So that's one of the drawback without having any cloud data, without having any data set. So here you will find I have my data set. So you can just also good. You have so many number of footprints. So what are there in white color? So those are all your Jedi footprints showing the Avogadro biomass density at that particular place. So all this is done, so you can apply those degrade flags if you want, but here I'm not applying because already I have few pixels in my region of interest. Why to lose that? So that's why I'm not doing that. So after doing this, you can composite, we take a median composite and you can click to your region of interest. So now it's done. My x-axis is there, my y-axis is there. So I want to switch to satellite based map. So you can just click map dot set options. This is the one function you can use for map dot set options to satellite mode. So automatically every time you run, it will be switched back to satellite mode, and you have your footprints within your image collection. So again, I'm turning this to false. So now my x-axis is ready, y-axis is ready. So now I have to sample for training of my dataset. So from here, I will sample the Jedi dataset. So you can just give the variable name samples is equal to, so whatever my input features are there. So input features, I will add these bands of my above ground biomass density, and I will sample the region. So you can just click on the sample. So here is asking what's your region of interest. It is my ROI. So what's the scale at which you want to sample? I'm giving 10 because most of my input features are at the 10 meter, though JR dataset is at 25-meter resolution. The Earth engine will manage itself and it will convert it into a 10-meter resolution. So projection and all is not needed. So factor is not needed. So number of pixels, let's give 1000 samples I have to get from this, and seed, random seed state I'm giving 5. So drop null has to be true because whatever uh, the Jedi dataset is there, it's only a footprint, so I have to drop wherever the Jedi dataset is null. So you can also give the tile scale to be 16, and geometries, does your feature collection has to contain the geometry, so just give true. If you don't want, you can give false. You can just close it and print your samples dot size. Click on the run. So it's computing. So I think my region of interest is quite big. So how about if we just reduce my region of interest? So because most of my data set are on this side, so you can just move it like this. That's it. You don't have to do anything. You just have to move your region of interest, and all of your data set is now is there. So now I have to click on the run. So you can also reduce your region of interest because it's taking more time to load. So since this is only a demo, so I want to reduce it a little bit. So yeah, this much would be enough, I think. So yeah, now you just click on the run. Yeah, I adjusted my region of interest just like in seconds. So what if you have a desktop software. So you have to again go and do every sample. So here you see my sampling size is 0. So because I have given drop nodes to be true, so you just remove this seed state and increase this to 5000 because it's just only a footprints, so it might not be getting enough points. So yeah, here you can see we have added the samples. So the sample sizes I have given the number of pixels to be 10 lakh. So 1 lakh, but the sample size is only 1000 because we have given the property true nulls to be true because wherever there is no above biomass density on the sampling pixels, so they will drop that. So only my valid pixels are 1007. So out of my 1007, now I have to split it for validation and training pixels. So just create valid training and validation set. So I'm going to create a variable called training and validation. So it has to be a random split because whatever the samples we have taken, so it has to be divided between training dataset and validation dataset. So training for training the model and validation for getting the validation of the model. So after training, so training and validation is equal to whatever my samples are there. I have to create a random column. So its name will be, by default it will be random, so I'm creating a random column and creating one more variable called training, and from my training testing, from my training and validation, I'm going to filter ee dot filter dot less than zero point 0.7 has to be, so you have to specify the column, this random column less than zero point 0.7 has to be in my training data set, and similarly for my validation set, training testing, so training validation has to be e dot filter dot greater than, you can give here less than or equal to, and here greater than this random zero point 0.7. So we just print training dot size as my training set, and you just print my validation dot size as my validation set, so that you can get how the split is done. So here you see, out of my approximately 1000 pixels, so I have taken 700 sets for my training the model and 300 for my testing of the model. So now it's time we train our model. So train the regression model. So I'm creating a variable called classifier. So here I have ee dot classifier dot smile random forest. So this is the machine learning algorithm which I'm using with the 500 decision trees. So I'm going to use the function dot train. So what is the features which you want to train? So this is my training, and the class property should be, I think it should be, I don't know, it should be a string or a classifier. So here you can just go to the documentary, so you need a classifier as an input, which we have given random forest as a classifier and a class property. It need a feature collection to train on, and it need a class property. So if you can see, the class property should be a string and the input property should be a list. So now it should be a string. So class property would be Avogadro biomass density. And input properties is my x-axis. So it has to be from my input features, you take the band names. So that would be a list of band names, and you don't need this subsampling and all. You can just close it. And for your region of interest, so you can just print this training dot first in order to know how the training data set is. So here you see feature, it has 24 properties, so it has a geometry. So if you can just expand the properties, here you will get all the band values at that particular pixel. So what they have sampled starting from B1 to B80 in our optical indices image, and we have our BH and BV, the Avogadro biomass density. So at that particular point is 134 tons for that particular pixels per hectare. So I have all the indices. So what I am telling this model is that, so you make use of this mild random forest machine learning algorithm. You use 500 decision trees and you train a model. So based on my training features which I have created here, so it has this much of properties, and you train on the y-axis, that should be a class property, my Avogadro biomass density, and on the x-axis, as my independent variable, I want all my input features and it band names to be used as on the x-axis. So one important thing you have to do here is that you have to set the output mode. Set the output mode to regression, because we are going to calculate the indices, so that's why. So if you can just go to here, set output mode for a classifier. So here you will see what are the different output modes we have. Classification by default, in order to carry out the class number, mainly for Lando's land cover classification. So regression, if you have a standard regression model, you have probability, you have multi-probability, raw regression. So you can go for all these output modes, but I'm using a regression function, the regression mode, to be output from my classifier. So this is only, this part is my model. So whatever you have done is the pre-processing for the model, whatever the inputs required for the model, only this part is there. This is my model which we are training. So now I hope this is clear to you. So what my training input has. So similarly, the validation input also has all this type of bands. So now I'm gonna just create a variable called Avogadro biomass density predicted, because I'm gonna predict now with the help of this training data. So Avogadro biomass density predicted. So for all my input features, I'm gonna classify with the help of this classifier, and you can just rename it as Avogadro biomass density predicted. That's it, done. Add this to map in order to know how does it look. Use some beautiful visualization parameters. So let's just say minimum is 0 and maximum value might be 500, and you get the palette to be red, white, green. Avogadro biomass predicted. That's it. Click on that. So here you can see your beautifully your Avogadro biomass density map is loaded. So you just expand this. So just get the zoom. So here you will get your map rendered. So whatever white color is there, it's having the low biomass, and whatever the green color is there, it's having the highest biomass. So this is our linear regression output. So it's just taking time in loading because it is at 10-meter resolution. So Google Earth Engine is taking time in order to load it. So you can just check and uncheck. So it is matching exactly with the base map. So wherever there is a barren land, there you can see the white patches. There is no above ground biomass density. So wherever there is high green covers are there, so it is depicting more above ground biomass density. So it just has to load properly. Yeah. So clearly you can compare. Our model has how it has worked beautifully. So this is how it looks. So if you had a larger region of interest, you may not be able to visualize that. So that's the problem. So that's why I reduced my region of interest. So if we can see the range, it is ranging from 24 megatons, grams per hectare to 267 megagrams per hectare. So here you can just change the values to 25 to 268. So that's how you can predict a model. You can build a model and you can predict the above ground biomass density without any kind of field data. So I hope you have understood how to do this and how you can get this. So one more question is that how accurate is my model? So whatever the values it is predicting, is that good? So how you can go for the accuracy assessment of the model? So this you will see in the next video for the accuracy assessment. And after the accuracy assessment, how you can improve the model with the help of hyperparameter tuning, and how you can improve the accuracy of the model. So we're going to use the various statistical metrics in order to derive the accuracy values, such as R square value, the coefficient of determination, the RMC value, the uncertainty errors, that is the root mean square error, and MAE value, that is also called as the mean absolute error. So this is how you can say that this my model is this much of accurate. My independent variables can predict the dependent variable. My model is this much confident based on the coefficient of determination with the help of R square value. And you can also predict the uncertainty values or the error margins with the help of RMSE MAE values. So that's how you're gonna do the uh, accuracy assessment of your model. So I hope guys you have understood how to do this, how to build your model. So this is just a part one of building your model. So then you just have to go for accuracy assessment and hyperparameter tuning and fine tuning your model in order to give the better accuracy. So I hope this is clear to you. So if you have any kind of doubts, queries, you can always post it in the comment section. So thank you for watching.